Hello and welcome to another Common Core Geometry lesson by eMathinstruction. My name is Kirk Weiler, and today we'll be starting a new unit, specifically Unit 8, which is known as right triangle trigonometry. Now that's a topic that you haven't had any exposure to yet, and so we're going to start off the basis of it today with lesson number 1 on similar right triangles. Now you're probably thinking to yourself, wait a second, I just finished Unit 7, that was all about similarity, what am I doing? Well, believe it or not, this whole unit is based on the idea of similar right triangles. And I'm not talking about those ones where we drew the altitude from the right angle to the hypotenuse and broke it up into two similar right triangles like we did in the last couple lessons of unit number 7. We're just talking about similar right triangles in general. So let's get right into those and talk about the lesson today. So here we go. Exercise number 1. Consider the two right triangles shown below, so ABC, DEF. Letter A says, how would you justify that triangle ABC is similar to triangle DEF? Be clear in your explanation. So why do I know that this right triangle must be similar to that one? Pause the video now and write down whatever you'd like. Hopefully something that's correct. All right. Well, there's actually a lot of different ways to justify that they're similar. All right. You could use a similarity transformation. I kind of doubt most people did that. Or you could use one of two different similarity criteria. All right. You could use the side-side-side criteria for similarity. All right. That's probably the one that's most obvious. In other words, the side-side-side theorem for similarity, not for congruence, said that if all three pairs of corresponding sides in two triangles were proportional to one another, then the two triangles were similar, meaning that if I take the 8 and I divide it by 4, I get 2. If I take the 6 and divide it by 3, I get 2. And if I take the 10 and divide it by 5, I get 2. Okay? And that really gets into that dilation constant that gives us similarity. In other words, I could dilate triangle ABC by a dilation constant of 2, and it would scale up to this triangle, right? Even the terminology, scaling. You could also say, though, that you could use the side angle side theorem for similarity. Again, for similarity, not for congruence, because we've got these two pairs of sides that are proportional, the 8, the 4, the 6, and the 3, and then we've got the right angles that are congruent in between them. All right. I still think this one is the best because literally it gets into that idea that one of these triangles is just a scaled up version of the other by a scaling or dilation constant by a factor of 2. Okay. Now, keep in mind, what we know about similar triangles is specifically that proportionality between corresponding sides. 8 divided by 4 is equal, 6 divided by 3 is equal, and 10 divided by 5 are all equal to the same thing. But now we're going to look at some different ratios. Ratios where we stick within the triangles. So letter B, very, very easy exercise, All right, what I'd like you to do is work through all of these ratios, and if necessary, because it will be sometimes and won't be other times, if necessary, simplify them. Write them in simplest form. Why don't you go ahead and do that? Take just a couple minutes. All right, let's go through. It's easy enough. BC divided by AB. Well, BC is 3, and AB is 4. BC divided by AB. Yeah, BC divided by AC. Well, BC is 3, AC is 5. And AB divided by AC, AB is 4, AC is 5. So there's nothing we can really do to reduce any one of these fractions. We could turn them into decimals, that would be fine. 0.75, 0.6, 0.8, what have you. But now, let's look at this larger right triangle. Here it asks me to do EF divided by DE. So that's 6 divided by 8, which of course reduces to 3 divided by 4. Then it asks me to do EF divided by DF, and that's 6 divided by 10, which reduces to 3/5. And finally it asks me to do DE divided by DF, which is going to be 8 divided by 10, which is, again, reduces to 4/5. And again, it may even be helpful to think about this in terms of decimals. 0.75, 0.6, 0.8, again, 0.75, 0.6, and 0.8. Now, what is clearly obvious from all of these is that these ratios keep turning out to be the same. And let's just take a look at this just for a moment, these two, right? When I did BC divided by AB, I took the shorter leg of this right triangle and divided it by the longer leg of this right triangle. And obviously when I did EF divided by DE, I did the shorter leg divided by the longer leg. So I did this divided by this, and I got the same thing I would if I did this divided by this. Now again, that's a little bit different than the similarity ratios we've been setting up so far. So far what we've seen are things like if I did this, 3, and I divided it by 6, I would get the same as 4 divided by 8. Now I'm sort of doing the division within the triangles themselves. 3 divided by 4 is equal to 6 divided by 8. And likewise, we could do the same thing. Here, BC divided by AB, that would be 3 divided by, BC divided by AC, 3 divided by 5 is equal to 6 divided by 10. Okay? We can summarize all of this in this one statement. The ratio of relatively positioned sides is equal between two similar triangles. They certainly don't have to be right triangles. The ratio of relatively positioned sides is equal between two similar triangles. Let's take a look at why that is in this exercise number 2. In the following diagram, triangle DEF is a dilation of triangle ABC by a scaling factor of k. Algebraically prove that DE divided by EF is equal to AB divided by BC. So again, keep in mind what I'm saying now is I'm saying if I take this side and I divide it by this side, I'll get exactly the same thing as if I take this side and I divide it by that side. Now, why is that? Well, let's kind of go through it. We can algebraically prove it quite easily, especially if we really understand what it means for a triangle DEF to be a dilation of ABC by a scale factor of k. You know, what does that mean? Well, it means that DE is equal to k times AB, right? The length of DE is k times the length of AB, and likewise, the length of EF is equal to k times the length of BC. So now, if I simply do DE, let me pull this up a little bit, if I do DE divided by EF, I get k times AB divided by k times BC, and that's k divided by k times AB divided by BC. I don't even mind the red dot right there, right? And then the k divided by k is just 1 times AB divided by BC, and there we have it. Now, what you can really think of this as is that the k is sort of like this constant that you divide out to simplify the fraction. You know how when you take something like, I don't know, 4/6, right? And you divide both top and bottom by 2 and you get 2/3. That's exactly kind of what's going on here. We're really dividing top and bottom by k, and we're being left with AB divided by BC. Now this is amazingly important because it allows us to set up proportions among similar triangles in a different way. Instead of saying, you know, a side length of this divided by a side length of this is equal to a side length of this divided by a side length of that, we're able to say, this divided by this would be this divided by this. The ratio of relatively positioned sides is equal between two similar triangles. Or we could say the ratio of relatively positioned sides in similar triangles are proportional. So now what we're going to do for the rest of this lesson is apply this version of similarity proportions as opposed to the ones that we've been seeing in the last unit. So let's go through some problems. All right, starting off with a very simple one. It says if we know that triangle MNP is similar to triangle EFG, and then they give us a bunch of different numbers, then it asks us which of the following is the ratio of EG to EF. All right, pictures, 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 draw pictures. And you might say, how can I draw a picture in this scenario? I don't really have an entirely good sense of what's going on here. Well, let's take a look. We don't have to draw a perfect picture. In fact, what I always try to do in a situation like this is I try to draw something quite generic. M, N, P, and then I'm going to draw a larger one. But I'm going to try to make it look kind of similar. Now I have to get the letters right. M, N, P, E, F, G. All right? M, N, P, E, F, G. They've got to be in the same order. What does it tell me? It tells me MN is 10, NP is 6, and MP is 14. Okay? And it wants the ratio of EG to EF. And again, the idea here is very simple, right? The ratio of relatively positioned sides is equal between two similar triangles. Well, if I want the ratio of EG to EF, that's going to be the same as the ratio of MP to MN, right? That's got to be MP to MN, and that's 14 to 10, which reduces to 7 to 5. Choice 1. All right? The ratio of relatively positioned sides is always equal in similar triangles. So even though I don't know anything really about EFG other than it's similar to MNP, if I want the ratio of EG to EF, that's the same as MP to MN. It's that simple. Let me step out of the way so you can write down anything you need to about this problem. Okay, let's move on. Now let's really kind of get into it. I even have my handy dandy 4-function calculator. Literally, 4 functions. That's all it does. Let's take a look. A person who is 68 inches tall casts a shadow that is 54 inches long. At the same moment, a tree casts a shadow that is 18 feet long. What is the height of the tree in feet? Round to the nearest foot, and draw a diagram to show how you are solving the problem. All right, let's do it. So you're going to get to see an illustration of my awesome drawing skills here. All right, so we have this person who has some issues, and we've got the sun. All right, and we know that the person is 68 inches tall, and they cast a shadow that is 54 inches long. Okay, it's pretty much that simple. Great. And the idea, of course, here is that we have a right triangle that looks like this, right? With the height of the right triangle being 68 inches and the base being 54 inches. At the same time, what happens is that we've got a tree, beautiful looking tree. All right, same sun. Just gonna draw it up here. And that tree casts a shadow that is 18 feet long. This is in fact a way that you could estimate the height of very tall objects by measuring their shadows, which are projected along a horizontal surface. Now, I would like to find the height of the tree. Why do I know that these two triangles are similar? Well, one, we make the assumption that both the person and the tree are standing at a right angle to the ground. That actually may not be a fair assumption if the ground is slanted, if the person is slouching, if the tree is leaned over, but we make that assumption. So they're both right triangles. But then the other thing is that the angle of elevation of the sun is the same in both cases. In other words, this angle and this angle are the same. So remember, all right triangles that have an acute angle that are the same are similar to each other. But now this is easy because I can literally say h is to 18. So if I take that height and divide it by its shadow length, I'll get this height. and divide it by its shadow length. Again, these two right triangles, assuming the right triangles are similar because the angle of the sun is the same in both cases. And now it's just an issue of cross-multiplying and solving, right? I'll get 54 times h is equal to 18 times 68, 1,224. Then I'll divide both sides by 54. And I can just do that right away. Divided by 54 equals 22.6 repeated. I want to know what the height of the tree is, round my answer to the nearest foot. So I'm going to say the height of the tree is 23 feet. That's it. Shadow problems are classic similarity problems. You could certainly have done this in the way that we did the other similarity problems. We could have done 68 divided by h equals 54 divided by 18. But in today's lesson, I'm going to keep sticking with sort of doing the ratio within the triangles and then extending it, right, or solving it using just simple cross multiplication. We're going to be doing a lot of cross multiplying in this particular unit. Not very much proof, I bet you'll enjoy that, but quite a bit of problem solving that involves cross multiplying to solve equations. All right, let me step back, take a look, copy down anything you need to, then we'll move on to the next lesson, or the next unit. Not the next unit or the next lesson, the next slide, next problem. I'm really looking to jump ahead quickly, apparently. Let's just go right on to the next unit. We're only into the first lesson on this one. Let's take a look at exercise number 5. A rectangular picture that has a width of 4.5 inches and a height of 3 inches. If the picture is to be scaled such that its new width is 6 inches, all right, what is its new height? What is the length of its diagonal to the nearest tenth of an inch? All right, fair enough. So let's take a look and draw a picture. Let's see what we're going to have. Okay, so we've got this rectangular picture. Okay, it's got a width of 4.5 inches. It's got a height of 3 inches, and you can appreciate this. I want to scale this thing up, right? I'm going to scale it up so the new width is 6 inches, and I'd like to know what the new height is. Okay? So again, I can stick within sort of like my rectangles. I can say that if I did h and I divided it by 6, I would have to get the same as if I did 3 and I divided it by 4.5. All right, simple as that. H divided by 6 equals 3 divided by 4.5. I can cross multiply. I'll get 4.5 times h is equal to 3 times 6, which is 18. I can now do, of course, 18 divided by 4.5, and I'll get h is equal to 4. What is its new height? All right, and its new height is just equal to 4. All right, let me get rid of that. The other part of this question asks, what is the length of the diagonal to the nearest inch? Well, this has nothing to do with similarity. That, of course, is just the Pythagorean theorem, right? So in that case, what I can do is I can just do a little Pythagorean theorem. I can say 4 squared plus 6 squared is equal to c squared. Right, I'll get 16 plus 36 is equal to c squared. C squared is equal to 52. And c is equal to the square root of 52. Unfortunately, my 4-function calculator doesn't actually have the square root of 52, the square root button on it. All right. I do know that it's got to be larger than the square root of 49, less than the square root of 64. Let me just take a look at something really quick. Since I don't have it and I don't really want to open up, let's see if it's 7.1. How about 7.2? Yeah, looks like it'll be 7.2. Right, 7.2 squared is very close to 52. We got 51.84. Good enough. We'll be opening up calculators that have all sorts of special functions on them, the TI calculator, in the next lesson, but to save us a little bit of time, we just do some estimating with our 4-function calculator there. All right, let me step out of the way again. Pretty easy problem, but write down anything you need to. All right, let's keep going. All right, final one. This is a classic use of similarity. It is difficult, most of the time, to measure the width of a river. Okay, a lot of times mathematics has some very solid uses, right? It's hard to measure the length of a river because, quite frankly, if you've got a very wide river like the Hudson River near where I live, it's kind of hard to extend a measuring tape across the river. You know what I mean? It's just hard to do that. Don't get me wrong, these days, of course, you can take aerial photographs, you know, if you have a scale on them, Google Maps, things like that. It's not as hard as it used to be. But it used to be that people would figure out the width of a river by using similar right triangles. Let's take a look at how that works in this problem. Exercise number 6. One of the classic engineering uses for similarity is the measuring of the width of a river. Not easy to do with a tape measure. To do this, engineers spot 2 points on opposite sides of the river, A and B. They then measure the distance of BD along the river and then a length of DE perpendicular to the river. Finally, they draw a line from A to E and mark the intersection point of AE and BD as point C. So the first part of the question is, explain why triangle ABC must be similar to triangle EDC. Why do those two right triangles have to be similar? Pause the video if you need to now and write down a small explanation. All right, well, let's do it. You can use a lot of different angle names. I think I won't number them this time, but the plain fact is the angle ACB, which is right here, must be congruent to angle DCE right there because they're vertical angles. All right, but any two right triangles that have equal acute angles are similar. Remember that from a few lessons ago? But even if you don't remember that, they've got those two angles equal, they've got the right angles equal, so they're similar by the angle-angle similarity theorem. So this is cool. This right triangle and that right triangle are similar. Now this is kind of cool. Let me give you the setup before we finish this off. Again, not so hard these days with aerial photographs, but literally it used to be very hard to measure this distance. What wasn't difficult though was measuring this distance. That could easily be done. This distance could easily be done, and actually the breakup of these two distances is also very equal. They're all on the ground, they're all on the same side of the river. You don't even have to go to the other side of the river. You just have to be able to spot points with telescopes and things like that. So let's take a look at how we find the width of the river. So now we're told, okay, BD is 225 feet. All right. We know that CD is 30 feet, all right? And we know that DE is 12 feet, and we want to find the width of the river. That's AB. I'll call it X. Now, one thing that we need is we actually need this length, and that's easy enough, of course, because we can just do 225 minus the 30, and of course, this length then is 195 feet, okay? And then we can set up the following ratio. We could say, well, X divided by 195, right? This divided by this would have to be the 12 divided by the 30. In which case now the numbers are going to get fairly large, but that's okay. We cross multiply. We get 30x 195 times 12, 2,340. Divide both sides by 30. And we have the width of the river as 78 feet. That's it. And again, it's kind of cool. It's sort of like the shadow tree, or the shadow problem with the tree and the person, right? It's very, very hard. Climb up to the top of a tree or a tall mountain or whatever, drop a tape measure down. Not so simple. On the other hand, measuring things along the ground horizontally is pretty easy. So in the old days, before Google Maps and satellite imaging and all of that, it was easy enough to measure all these distances on the same side of the river and then use similar triangles to calculate the width of the river. It's kind of neat in that way. Anyway, let me step back for a second, bring this back up, let you write down anything you need to, and then we'll wrap up the lesson. Okay, let's move on. So, the major takeaway from today is very, very simple. If you've got two similar triangles, and for the rest of this unit we are only going to concentrate on right triangles, nothing but right triangles, the ratio of relatively placed sides will always be equal between the two similar triangles. So for instance, if you have two similar right triangles and you do the short leg of one divided by the hypotenuse of the same triangle, that will give you the same number as if you do the short leg of the other divided by its hypotenuse. Okay? Whenever we look at the ratio of relatively positioned or placed sides, that will stay consistent amongst similar triangles, whether they're right triangles or other. But from now on, we're going to stick with right triangles. And we'll get into that in the next lesson as we start to introduce right triangle trigonometry. For now, though, I'd like to thank you for joining me for another Common Core geometry lesson by eMathinstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.